Hi, in this video, I'm going to explain about a late code problem 2503, maximum number of points from grid queries. In this question, we are given as a m into n grid. We want to process k queries. Okay. Each queries we want to answer independently. The queries, in each query, we have a value. We want to travel from the top cell of the grid and which is less than the value. For example, we are given a grid and we have three queries. The first query is value is 5, which means we are starting from top cell and we can go any four direction, top, left or right and down. We cannot able to go outside of the grid. And we can only move to the cells which are less than the less than the query value. For example, we are currently in one cell one, uh, then the value is 2 from right side of the cell, which is less than the 5, and right side which is value is 3, so it's also less than 5. And the same way we can also move to the downside also, is 2, and we can also move to the value 3, but we cannot able to move to the value which is right side of the 2 because its value is 5, which is greater than or equal to the query value. The same way we cannot able to move to the value 7 because it is greater than or equal to 5. The same way we can also move able to move this cell. So this is so finally our travel is ended here. So the answer for this query is how many cells were visited. We are visited 5 cells, so this is the answer for this query. The same way we want to process next query, this is independent, so we want to start it from we want to start this process from again top cell. The same way we want to travel in this process, we can able to visit all the nodes except 7. And the next one is query value is 2, so we can only able to move one from the top cell. We cannot able to move to the right and down, so the way only visited cells are 1. So the same way we want to process the each queries, and we want to find the maximum number of cells we can each able to visit for each queries. The query length can up to go to 10 power 4 and the query length value, and the number of grid cells can go up to 10 power 5. So let's explain how we can solve this problem. Okay, now let's see the algorithm part. We see the algorithm by dry running with an example. So I take a bigger example one, which is a 4 cross 4 grid, and the query is 468. So instead of the key concept is we are going to use the algorithm which is 3D. Instead of processing each query value, we're going to process all possible values, and then based on our processing, we are going to answer for each query in time complexity order of 1. So let's see the algorithm. First, we are going to insert our first value into our queue and mark as a visited. The queue is priority queue, which is min heap. So we're going to insert one into our priority queue, and we are going to explore its neighbors. So this is the normal BFS approach. We can visit all neighbors which is in the 4 sides. So you can add 7, and we also mark this as visited, and next is 2. Okay. Before visiting its neighbor, we want to do one biggest operation, which is we want to find the max bound value. What is max bound? The max bound will say that to reach this cell, at least we want to this much amount of value. So this is nothing but initially it will be 0, because to reach the cell 1, we need no values. To reach means before reach 1, we does not need any bound, any values. So to reach 1, we need at least value which is greater than 1. So max bound will be 1, because the maximum of 0, 1 is 1. So to visit cell 1, we need at least value which is greater than 1. Next, so we visited 1 and updated the max bound 1, and we want to also increment the 1's value. So it is initially 0, we update this to 1. So next we are going to explore its neighbors, which is minimum, because it is a min heap. This 2 is the minimum, and we pull out from the queue and add his neighbors into queue. So it is 3 and 8. So it is not visited yet. And we also check whether our max bound is incremented or not. Yes, it is incremented, because initially the max bound is 1. Now it's incremented to 2, which means to reach these cells, To reach this cell, we need at least a value which is greater than 2. So we want to also increment the bound value of 2 to 1. The next one is next minimum value is 3. We are going to pull out this value from our priority queue, and we are going to visit this neighbor, which is 5, and this 5. We add this value into our priority queue. Okay. We also check whether it is going out of bound. It is incremented our bound. Yes, it is incremented our bound. So our max value become 3 now. So we increment the 3 value to 1. Next one is next minimum value of the in priority is 5. We pull out this 5. Maybe can any 5, this 5 or this 5. So I'll take this 5 and its neighbor is 1. To add the neighbor. Now we check whether our current value is greater than our max bound or yes. If it's greater than max bound, we update the bound into 5 and remove this values. Now this value is updated to 5. So now I going to increment the 5 value into 1. Now again I going to explore the minimum value which is 1. So I'm going to explore its neighbor which is 3. I'm going to mark this 3 as a visitor and they put it in the queue and they pull out the 1. So I will check this compare this with max bound which is 5 but the current value is 1. So this is the key point. Still this value is 1. We cannot able to reach this 1 without without the query value which is greater than 5, because there is a boundary, because this 5, 5, 8 and 7 this act as a boundary which is prevent us from visiting 1 without less than without the query value less than 5, less than or equal to 5. At least the query value greater than the 5, then only we can able to reach to 1. This is the to track this bound value, we use the max bound keyword. So this is the key approach here. Then I incremented them. So now I incremented the bound of 5 into value of 5 into 2, because if the value is greater than 5, we can able to reach this cell. And the next minimum one is 3. I pull out this 3 and add neighbors into queue. So 3, 4, and this value is updated to 3. And I pull out the next minimum value is 3. I remove this value from the priority queue and compare this value into maximum or not. The 5 is the maximum, so I will update the 5 into 4 and I explore these neighbors, which is 7 and 5. 7 and 5 and remove this 7 from 5. Next one is minimum value is 4 and remove this 4 and check whether the 4 is greater than the bound or not. No, so still is a 5, so I increment the bound value 1. So next the minimum value which is 5, this 5. And these neighbors, all neighbors are visited, so I cannot able to add any neighbor into priority queue. So this is 5. And the next value is next minimum value which is another 5 is there. This so this 5 we consider this this 5 and we add the 6 neighbors neighbor 6 into queue. I think this value is 6 because we forgot to update that, and then we check the bound whether the 5 is greater than or not, greater than the max bound or not. It is equal to the bound, so we don't change it and update this bound to 7. And we add the 6 into queue. So we did this. So the minimum value in the currently in priority is 6, and remove load the 6 and add the neighbors into priority. So this 3. So after we check whether the max bound is greater than max bound need to update. Yes, it need to update. We can change it to 6. Now the max bound is 6. We update the incremental frequency of 6 into 1, and we reach the next is we reach minimum value is 3, and we visit its neighbors, which is 3 again, and we mark this visitor and remove this, and we increment. We check whether the max bound is greater than or not. So it is greater than, but our current value is 3, so we cannot able to update and increment the bound frequency. Next value is in the priority is 7. So 7's neighbors are already visited. We check the bound is whether the bound is go out of bound. Yes, we want to update the bound to 7. So increment this frequency to 1. And the next unvisited node is again another 7 is there. And we check whether we need to update the bound or not. No, so still we increment this value to 2. and the next value is switching is 8. So we update this value to 8 and increment this frequency. So this table will say that to reach this, for example, with the to to process our queries, we want to find the prefix sum of this. So prefix sum is 1, 2, and 3, 3, and 10, and 10 at 12. I think this could be 3 because after 6 we can work to visit the 3 and 3 again 3 times. So I forgot a bit one time, so it's 3. So now this value could be 10 plus 3, 30, and 15 and 60. Okay, I forgot to update this value because after we visit 6 and we update the 6 and we visit 3 next and next 3. So I forgot. So 6 value can be 3. So this is the prefix array 1, 2, 3, 15, and 10, and 13, 15, 16. So based on this prefix array, we're going to answer the question. So the prefix array will indicate that for 3, if the value is greater than the 3, we can get up at least 3 points. Okay. So that just verify whether the correct answer. The value is 4. So which is greater than the so the value is 4. We can get it is greater. It is plus 1 of this 3. So we will verify. If this value is 4, we can get this amount of points. So this is correct. Next 6. The value is 6. We can get n minus 1. 6 minus 1 is 5. So which is 10. We can get up to 10 points. So we will check the value 6. We can go. We can visit this. Also we can visit this, and we can also able to visit this. So the 6 and this, so it's correct. So this is also 10. So this is also correct. Next is 8. The value is 8. We can visit 8 minus 1 7. So it is 15. So it's also correct. You can also visit this, and you can also visit. You can go to these points, but we cannot able to visit this. So this is also correct. So this is the key approach to solve this problem. So let's see the code of this algorithm. Okay, let's see the code. In the first line, I declare the director array, which is used to indicate the direction where from the current cell where we can go. It is always we use in breadth first search concepts. So this is the direction array to visit the 4 neighbors. And the next one is the matrix, which is visitor matrix, which is used to track whether we already visited the cell or not. And the next one is priority queue, which is used to I already said we want to track the minimum value always. So to track the minimum value which is we already visited, we use the priority queue. We take the priority queue of vector of priority queue. Vector as a data type because we want to track three values. One is grid cell and the grid cell value, and next is the row of the grid cell value and the column of the grid cell value. Because to visit its neighbors, to take out we take out the value and we want to visit these neighbors. So we take the 3 values. We take 3 values in the vector. Next, we mark visit as the initial cell as true. And next I declare the another variable which is called dp, which is I used in we said frequency. We used to track the frequency of the values. And the next one is max. I declare another variable which is max. Initially it is 0, and I put the initial value into the grid, and then I start my normal DFS approach, DFS process. I take out the top of the priority value and store the current row value and current column value into the R and C variable, and current cell value in the parent variable. And I will check which is the maximum one. Then I did increment the frequency, and then I visited his neighbors. If the neighbor is out of bound or we already visited the neighbor, I will skip the iteration. Otherwise, I add into the priority queue and mark the neighbor as a visitor. Then I will find the prefix sum of the visited prefix sum of the frequency array. Then I will process each query. For each query, I want if the value is 5, I want to add the value of 4 because till 4 we can reach, because we can only move up to less than the query value. If the query is 5, we can move the cell which is values less than 5, which is 4. Up to 4 we can only move, so that's why I use the -1, then I return the answer. So this is the uh, code for this, and the time complexity could be order of n cross m into log of n cross m, because we visit every cell and we use the priority queue also. So this is simply it is order of number of cells in the grid into log of number of cells in the grid. And the space complexity could be order of n square, because we use the visited array extra, and also you used one of the DP array. So this is the idea about this problem. Let me see in the next another interesting video. Bye.